So before anything else, let me introduce to the topical workbook for computer science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now.
Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another physics lecture. I hope you guys are doing fine, and inshallah today we are going to wrap up the new syllabus for physics as we are down to our last topic. In the previous lecture, we started off with 6.2 stars in the universe, and we dealt with around half of it. So without further ado, let's move on to the remaining topics in this section. The universe. The Milky Way is one of the billions of galaxies that make up our universe. The diameter of the Milky Way is around 100,000 light years, and it contains around 800 billion or more stars. We say that it contains 800 billion or more because obviously the distance to cover entirety of Milky Way is so big, 100,000 light years, that it's just not possible for human technology to capture it all yet. Redshift. As the universe expands, it stretches the wavelength of light along with it, and this process is known as a redshift. The farther away an object is, the more the light from it has stretched by the time it reaches us here on Earth. So it basically moves towards the red part of the visible light spectrum that is known as a redshift. Stretching over distance makes a redshift one of the key tools for measuring the universe and finding how much far away an object is from us, or at what rate it is moving away from us. Since astronomers can usually determine what wavelength they would see from up close, they can tell how far a galaxy is by how much the light has changed. As you can see, this was supposed to be an original pattern, but it has shifted over here, signifying that a redshift has occurred, signifying that the object from which this light is coming is very much far away. Distant galaxies have all of their visible light shifted into infrared because they are so far away that their visible light can't really reach us. It rather reaches us in a form of infrared only. The interpretation of the redshift is based on Doppler effect. Now, Doppler effect is something we usually associate with sounds. It occurs with sound waves and explains the rise and fall of pitch of a siren as a vehicle or an ambulance approaches us and passes away. If something is getting closer to us, we would hear the sound becoming louder, and as it would pass through us and move away, the sound will eventually drop down, and ultimately we would cease to hear it. The same effect is shown by light. Something that is moving away from us, its visible light tends to shift away in the infrared zone. The opposite can also occur for a galaxy that is coming towards us, or for an object that is coming towards us in a phenomena that is known as blue shift, but that's not really a part of your syllabus. So anyways, when the light source is receding, the wavelength seems longer and the light is more redder in appearance. As you can see, if you have a nearby galaxy on the spectrum, when you go for a spectroscopy, you would see a spot like you would see a pattern like this, and if the galaxy is moving away or it is distant, instead of this line you would see the line slightly shifted towards the red area. If a galaxy or a star is very distant, then there would be a much larger redshift towards the infrared size. From the size of the redshift of a starlight, the speed of recession of the galaxy can also be calculated. The most distant ones visible are receding with speeds up to 1/3 of the speed of light. The redshift in the light from distant galaxies provide evidence that the universe is expanding at a steady rate, and it supports the idea for the Big Bang theory for the formation of the universe, that before a certain amount of time, all of the galaxies and all the matter was at the same place together, and then some outward explosion occurred that caused the galaxies to move away, the matter to move away from each other, and as the after effects of that explosion, the Big Bang, the galaxies are still moving away from there, or instead of being positioned at a fixed point in the universe. Here's another image to make you better understand the concept for the redshift. If a source is at rest, then and the observer is also at rest, then you would see steady wavelengths. If the source is approaching you, the wavelength would be getting smaller as the frequency and pitch would rise, whereas if the source and the observer are receding away, they are going further away from each other, then the frequency and pitch will fall and the wavelength will become longer, or the visible light would move towards the redder area of the electromagnetic spectrum. The Big Bang theory. If the galaxies are receding from each other, it follows that in the past they must have been closer together. It is therefore possible that initially all the matter in the universe was packed together in an extremely dense state. The Big Bang theory proposes that this was the case, and that the universe started about 14 billion years ago from one single place with a huge explosion, the Big Bang. The resulting expansion of universe continues even today. Now that's everything you need to know as far as your syllabus content is concerned. Now let's have a look at some of the example questions. Okay, the sun emits energy in the form of electromagnetic radiation. Which three components of the electromagnetic spectrum account for almost all of this energy? Infrared, microwave, and ultraviolet. No, not ultraviolet. Infrared, microwave, and visible light. Okay, close, but we don't have microwave either coming from the sun. Infrared, ultraviolet, and visible light. Yes, that's the correct answer, because these three things are the ones that our sun emits the most. We have discussed that in our previous lecture where we discussed the sun as a star. When in the life cycle of a star are the heavy elements produced? When a cloud containing hydrogen collapses, no, that kind of forms a protostar. When a protostar becomes stable, no, at that time fusion starts, but only helium is formed technically. When a red supergiant explodes, yes, like we studied in our previous lecture, when a supergiant explodes, a lot of new elements are formed, which are heavier. The statements J, K, L, and M describe different stages in the life cycle of a star. J, a cloud containing hydrogen collapses due to gravitational attraction. Okay, that should be the first stage in the life cycle of a star, because we are basically discussing a nebula is forming a protostar. A red giant is produced. No, that's kind of the last or the second last stage. A white dwarf is produced. No, that's the absolute last. Hydrogen undergoes nuclear fusion to produce helium. Okay, that should be the second stage. Then the third one should be a red giant is produced, and the fourth one should be a white dwarf is produced. So it should be J, M, K, L, and that sequence is given in option A. So A would be our correct answer. What provides evidence for the Big Bang theory? The expulsion of heavy elements into space during a supernova explosion? No. The increase in the observed wavelength of radiation emitted by distant galaxies? Yes, we just discussed that. This is known as redshift, and it is an evidence for the Big Bang theory. I have deliberately included more questions for this section, as this is a new topic for the physics O-levels and IGCSE syllabus. So obviously you would be worried about what type of questions would be appearing in your paper. That's why, in order to relieve your stress, I have deliberately added more questions for this topic. A planet is in orbit around a distant star. As it passes in front of the star, it blocks some of the light of the star from reaching Earth, reducing the brightness of a star as seen from Earth. Figure 3 shows the view from Earth as the planet passes in front of the star. This is the star and the planet is revolving around it like this. Figure 3.2 shows an incomplete graph of how the brightness of a star varies with time as seen from Earth. So and the planet is in front of the star from time t1 to time t2, means the time it takes the star to move from over here to over there is t1 to t2. Now you have to complete the graph. What you need to do is, when this is the normal brightness of a star, so when this planet would be moving in front of the star, the brightness would be reduced. So that means you'll draw basically something like this, like it's shown over here, and as you reach T2, the line would become at its previous level, because now the planet is not in front of the star and you are getting full brightness from the star. Describe how the completed figure 3.2 would be changed to show a larger planet passing at the same distance in front of the same star. Well, if a larger planet is moving in front of the star, then that would mean that it would block more of the light coming from the star between time t1 and time t2. Hence the brightness of the star would be lowered to even a reduced level. It would drop down to somewhere over here, and after the star is passed, it would go back to its original position. So the time to reduce brightness and time to increase brightness would also be longer as the planet is bigger, and you would have to draw something like this. As you can see, now this graph is just for your understanding. You don't have to draw it in this question. As you can see, this time the brightness shown is lesser during the planet's passing. Suggest how an astronomer uses the changes in the brightness of the star to measure the orbital period of planet around the star. You simply measure the time between t1 and next t1. The next time the star's brightness start to decrease, or the time between t2 and the next time the star's brightness starts to increase or comes back to its original level after dipping down. That would give you an idea about how much time it takes for the planet to rotate around a star. When astronomers look at distant galaxies, they find that the frequency of light from galaxies shifted towards the red end of spectrum. And apart from visible light, state two types of electromagnetic waves that contain most of the energy emitted by a stable star. Obviously, only two possible answers over here: infrared and ultraviolet. Describe what is meant by the red end of the spectrum. It is the end of electromagnetic spectrum with the longest wavelength or the lowest frequency, as discussed above. The speed of recession of a galaxy is the speed at which galaxy is moving away from Earth. Astronomers use redshift to measure the speed of recession. Astronomers can also measure the distance d of the galaxy from Earth. Such large distances are always written in light years. Astronomers can estimate the time t that the galaxy has been moving away from Earth using the equation t equals to d over speed of recession, or basically time taken equals to distance upon speed. Table 4.1 shows their estimates of 4 different galaxies. This is the value for distance, this is the speed of recession, and this is the time in billions of years. State what is meant by a galaxy. Obviously a collection of billions of stars. Show that 1 light year is equal to 9.5 into 10 to the power 15 meters. There are 365 days in a year and 24 hours in a day, and we know that light travels at a speed of 3 into 10 to the power 8 per second. This is in meters, so we just multiply it with 365, the number of days in 1 year, then we multiply it with 24, the number of hours in 1 day, then we multiply it by 60 because that's the amount of minutes we have in 1 hour, and then we multiply it by another 60 to convert it to make it so as we have 60 seconds in 1 minute. So now we are basically multiplying the speed of light per second with the number of seconds which are which are available. This multiplication would give you the number of seconds available in a year, and when you multiply it with the speed of light per second, you get your final answer, that how much light travels in 1 year, and that comes out to be 9.46 into 10 to the power 15, or you can round it off to 9.5, hence proved. Describe the relationship between speed of recession of a galaxy and its distance from Earth. Further the galaxy is from Earth, the greater will be the speed of recession, or speed of recession is proportional to distance from Earth. Explain how the value of t provides evidence for Big Bang. When you look at the table, all values of t are literally the same. They are all nearly 13 to 14 billion years old. The time period taken for all of them is roughly 13 to 14 billions of years. So that means all galaxies and the Earth were together 13 to 14 billions of years ago. Some stars are initially much more massive than the Sun. Describe the life cycle of such a star after it has passed through the stage of being a protostar. After the protostar, the star would become a stable star, and then it would expand to become a red supergiant, and then it would become supernova and throw off outer layer into the space, forming heavier elements. The core would then become a neutron star, or it would become a black hole. As you can see over here, we had this diagram to make it understand as well that for the massive star it would become red supergiant, then a supernova, and then either it would become a neutron star or either it would become a black hole. Okay. although the early universe contained only light elements such as hydrogen, it now contains a number of very heavy elements. State in which part of the life cycle, again this roughly the same question. Newer, heavier elements are formed due to reactions in a supernova. That's the only possible answer, especially for 1 mark. You don't need to write anything else. So there you go. Alhamdulillah, we have absolutely covered each and everything for physics O-levels or IGCSE according to the new syllabus. So I hope you have understood everything. If you have any problems, feel free to comment them down below. Do let me know how did you like this series of lectures for physics. And one more thing, if you would like to order a hard copy of all these notes which I have compiled, then you can contact me on the WhatsApp number that's written below in the description. And that was it. I hope to see you guys in a new video with a new topic, maybe some other O-level subject, or I might as well go back to my yearlies for O-levels computer science. That's my main subject. Till then, I'll see you guys in the next video inshallah. Take care. Allah Hafiz.